Welcome to a video lecture or a screencast that will be about organic chemistry, and this is going to replace the class that was missed on April 28th. Let's start by remembering the demonstration that was done in class on Tuesday. This is powdered sugar, and we added to that some sulfuric acid, and the mixture started turning black and steaming, and then this sort of black solid material, but not very dense solid material, grew. A bunch of steam was given off. It was kind of gross looking. And anyhow, this was a very distinct chemical reaction that occurred. And the black substance that was made was actually kind of crumbly, and it's in fact carbon. And the steam appearing stuff that was given off was in fact steam or water. And it's kind of an interesting but gross looking perhaps product from this reaction. And anyhow, table sugar, which was our starting material, which was our source of carbon, is what's called an organic chemical compound. Now, organic means a lot of different things to non-chemists, but to chemists, an organic compound is one that contains carbon. Doesn't have to do with being natural, doesn't have to do with being made with no pesticides or herbicides, just means it contains carbon. Now, a little bit of history, going back to the 1800s, a guy named Friedrich Wöhler made urea in his laboratory. Urea is a component in urine, of course, and he made it from ammonium cyanate, which is what we would now call an inorganic compound. It was didn't come from living material, and the reigning theory at the time of Wöhler was that living substances had some sort of vital force that non-living substances didn't have, and that's what made living things special. And by making urea, and it was believed that there was no way to make compounds or substances found in living organisms without the living organism. Wöhler overturned this vital force theory by making something produced by living organisms, i.e. urea, from something not produced by living organisms or not using a living organism at all, which was the ammonium cyanate. So anyhow, he was essentially the father of organic chemistry in a way. And going back to the example and kind of tying together these two ideas, table sugar contains carbon, which we saw that black stuff appear, hydrogen and oxygen, which were given off as steam, and it contains carbon, hydrogen, and oxygen in about a 1 to 2 to 1 ratio. Now, this is the reason table sugar is what's called a carbohydrate. It contains carbon, and it contains hydrogen and oxygen in about the same ratio as in water. Now, this isn't to say that table sugar is exactly made up of a carbon with a water molecule stuck to it and another carbon with a water molecule stuck to it, etc. The arrangement of the atoms is different than that, but it's the same ratio. And more on that, more on structure in a bit. Now, there's all kinds of examples of organic compounds. Some important ones to us are byproducts of petroleum. So gasoline, mineral oil, lubricating oil, and petroleum jelly are all shown here. All carbon-containing compounds, all, in this case, actually did come from formerly living organisms that decomposed and produced these materials over eons of time. But anyhow, organic chemistry to us is going to simply be the study of carbon compounds and the properties of these carbon compounds and the reactions these carbon compounds undergo. So that's organic chemistry. Okay, it equals carbon chemistry. And now let's go into the chemistry a little bit. Well, as we started to do earlier in the week, carbon atoms have 4 valence electrons, so they can form 4 bonds. And they can form strong bonds to many other elements, including themselves. They can form long chains, and they can form branched molecules. We'll go into all of these aspects in much more detail soon. Carbon tends to form bonds with other carbon atoms, with hydrogen, with oxygen, with nitrogen, with sulfur, with lots and lots of things, primarily other non-metals. Some examples of carbon compounds. The one we've already seen, the simplest carbon compound, is methane, a carbon atom bonded to 4 hydrogen atoms. Here is what's called ethane, 2 carbon atoms. Each carbon atom is bonded to 3 hydrogen atoms, so each carbon makes 4 total bonds. One of the bonds is to another carbon, and the other 3 bonds are to hydrogen. Well, here's the 3 carbon with hydrogen molecule. This is called propane. It's got 3 carbons, not quite in a line. It's actually got an angle from carbon to carbon to carbon. But each carbon makes 4 bonds, either to 1 or to 2 other carbons, and to either 2 or 3 hydrogens. And let's jump to a more complicated compound. Here's nicotine. All of the darker gray atoms represent carbon, the blue atoms represent nitrogen, and the sort of off-white atoms represent hydrogen. Now, we can have much, much more complicated organic compounds as well, but this is kind of a good starting point. So here's a little bigger picture of nicotine. Well, let's start our work through organic chemistry with the simplest type of organic compounds, what are called hydrocarbons. They contain carbon and hydrogen. And the simplest type, or the starting point for us for hydrocarbons, are what are called alkanes. And what makes something an alkane is it's a hydrocarbon where all the carbon-carbon bonds are single bonds. Some examples of hydrocarbons with single bonds to carbon between carbon atoms. The simplest alkane is methane. There's actually only 1 carbon, so there's not even another carbon to bond to, whether it's single or not. And here are some more alkanes. These are 1 carbon, 2 carbon, 3 carbon, 4 carbon, etc. Molecules. 1 carbon is methane, 2 is ethane, 3 is propane, 4 is butane, etc. For many of these, you can see the prefix tells you something about how many carbons are in that, what are called straight chain alkanes if the carbons are in a row. So for example, hexane, hex is the prefix for 6, so hexane has 1, 2, 3, 4, 5, 6 carbons in it. Notice here the molecular formula has been shown in kind of expanded form, rather than just saying, okay, there's 6 carbons, so C6, and then however many hydrogens, and if you add them up, you'll see there's 14. We're actually showing a little bit of the structure in terms of how these atoms are connected together. So these are often called condensed structural formulas for that reason. It shows we have a carbon bonded to 3 hydrogens, that's bonded to a carbon bonded to 2 hydrogens, that's bonded to a carbon bonded to 2 hydrogens, etc. Another one, and then finally that's bonded to a carbon with 3 hydrogens attached to it. Let's do a little bit about the properties of alkanes, and we'll look at properties of organic compounds in general, but often it helps to look at a specific type of organic compound. So alkanes are all the same in that they're all made of carbon and hydrogen. All the carbon-carbon bonds are single. How they differ, we can go back to this picture here, is 1 carbon, 2 carbons, 3 carbons, 4, etc. on up here through decane, which has 10 carbons. So how they differ is they simply get bigger as we go from less carbons to more carbons. These are non-polar molecules because carbon and hydrogen both have fairly similar electronegativity, so they don't differ very much in how much they attract electrons. So they do not have positive and negative regions. They're non-polar. They still interact with each other. They still have attractive forces, even though they are not polar. We'll talk about these forces more later. But for now, the thing you can see from this graph, which is of number of carbons versus boiling temperature or melting temperature, is as we get more and more and more carbons, the temperature at which the substance melts goes up gradually, and as we get more and more and more carbons, the temperature at which it boils goes up gradually. Basically, the bigger molecules have bigger attractions between them. Therefore, it takes higher energy to overcome those attractions and to make the molecules either separate from each other just a little bit and be free to move around as we go from solid to liquid, or separate from each other a lot and turn into the gas phase as we go from liquid to gas. So the strength of the attractions between molecules is shown by the increase in melting and boiling point as we go from smaller molecules to larger molecules. And this is actually an important application of these different attractions between molecules and different boiling points of the different alkanes, different carbon chains, because this is how we distill crude oil. So crude oil, when it's pumped out of the ground, is a mixture of hydrocarbons. Some of the hydrocarbons are smaller ones, 1 or 2 or 3 or 4 carbons. Some are larger with more carbons. Some even will have 16, 18, 20, and more carbon chains. They differ in their boiling temperature, so we can separate them by what's called distillation, where we pump crude oil through a furnace. It's heated up. It goes into what's called a fractionating tower. And basically, the bottom of this tower is higher temperature, it's hotter. Top is cooler, lower temperature. And so at the higher temperature, pretty much all of the different carbon compounds have been turned into a gas. And as it goes a little higher, or when we're near the bottom of this, as we go to a little bit cooler temperatures rising, what happens is the bigger compounds will condense. If we go a little higher in the column to lower temperature region of the column, then the smaller molecules will be able to turn from gas into a liquid and condense. And we keep on going higher up, lower temperature, smaller yet molecules will condense because it doesn't take as much energy to keep those separated. It doesn't keep as high a temperature to keep them in the gas form. So then they'll start condensing, and higher up yet. And basically what happens is we can then separate the big molecules from the slightly less big molecules, from the middle-sized molecules, from the somewhat smaller molecules, from the really small molecules, on the basis of their different boiling points. So these guys require higher temperatures to stay a gas. These guys will stay a gas at fairly low temperatures. So that is hugely important to us because we use the separation of petroleum into its components in lots and lots of different ways to get gasoline to drive our cars. Here's a oil rig out in the ocean. Here's pollution from our huge use of petroleum. But anyhow, our world runs on, at least so far, petroleum and the energy that comes from burning it. And that's worth noting as well. Hydrocarbons, part of why they're useful to us, actually maybe the biggest reason they're useful to us, is they burn well and produce energy when they burn. So hydrocarbons undergo combustion reactions. We've seen these before. This is propane, C3H8, reacts with oxygen. That's always needed for combustion. And combustion of hydrocarbons, if it's complete combustion, produces CO2 and H2O, and then we've balanced the equation. Now, as we move to more complicated organic compounds, we need to consider something that actually has been talked about in class already, which is illustrated here by a chlorine atom. It has 7 valence electrons, and one of its valence electrons is not paired with another valence electron. This is something we call a radical. Radicals are very reactive. This is a chemical radical, that is. And hydrogen, the OH group, CH3, are all examples of radicals which have unpaired electrons, and because of this, these substances are all very reactive. And here is an example of what's called a methyl radical, carbon bonded to 3 hydrogens. Since it's not bonded to a 4th hydrogen, there's an unpaired electron. Here's another methyl radical, and hopefully you can see, here's an electron, needs to have a partner. Here's an electron, needs to have a partner. Match made in heaven. They can combine, and that makes the 2-carbon alkane called ethane. And we can essentially build up into longer and longer chain molecules by combining these little fragments like methane or methyl radicals. And here's a picture of an ethane molecule, and make longer and longer chains. One other thing probably worth noting here is actually let's go back to this one. This is the Lewis dot structure for ethane. It shows how the atoms are connected, carbon to 3 hydrogens, carbon to 3 hydrogens, and then carbon to carbon. It doesn't show the shape very well because we drew this on a flat piece of paper here on a flat computer screen. This is a somewhat better image in terms of seeing the 3-dimensionality of the carbon, where you can see that the 3 hydrogens and the 1 carbon don't form a flat sort of X or plus shape. It's actually 3-dimensional. And then we often also show these sort of images, which shows the real shape of the molecule a little better, because real molecules are not balls and sticks connecting the balls. It is actually more like a sphere where the electrons are zooming around in here for the hydrogen atom, zooming around in here for a hydrogen atom, zooming around in here for the carbon, and then they're zooming around in between there to hold these things together. So these are other representations that we often use. These are called space-filling models, and these are a little better representation of what the electron clouds would look like. Okay, so here is the add 1 more carbon, add 1 more methyl radical type of thing. This gives us propane, C3H8, and of course we can keep going, and here's the 3-dimensional view of propane. You can see the bond angle between carbon carbon is actually bent. In case you're interested, that's about 109-degree bond angle from carbon to carbon to carbon, and about the same from hydrogen to carbon. Oops, let's go back there. About the same from hydrogen to hydrogen, etc. Okay, so the process can continue. We get the straight chain alkanes as we've seen already. Let's note the relationship between the carbon and hydrogen in terms of numbers. 1 carbon has 4 hydrogens, 2 carbons have 6 hydrogens, 3 carbons have 3 plus 2 plus 3 is 8 hydrogens, etc. And you might go through these and check, but the formula for an alkane at least is always going to be whatever the number of carbons, twice that number plus 2 more equals the number of hydrogens. So check that out. For example, octane has 8 carbons. Twice 8 is 16. Add 2 more, that's 18. And you should, if you check through here and add them all up, find that there's 18 hydrogens in a molecule of octane. So that's C8H18. Okay. A little bit more on the shape of straight chain alkanes. This 3-dimensionality we've talked about, this 109-degree angle between the bonds. This is what's called a tetrahedral shape. Tetra means 4, and it's actually not called tetrahedral because there's 4 things attached to it. It's tetrahedral because a tetrahedron looks like this. It's a pyramid with 1, 2, and then on the back 3, and on the bottom 4 sides. So that's the reason for the name tetrahedral. All right, propane, and let's move on. Now, there are also what are called cycloalkanes, and it's kind of what it sounds like, Cyclo means circle or ring, and alkane means all carbon-carbon single bonds. Now, notice when we make a cycloalkane, so for example, prop means 3, propane means all single bonds between carbon atoms, and if we put the 3 carbons in a ring, then each carbon is bonded to 2 other carbons. That's 2 bonds. It only has 2 more bonds possible to make, so it's bonded to 2 hydrogens, and what we end up having is 3 carbons and 6 hydrogens, so less hydrogens than if it was in a straight chain, not bonded in a ring. One other thing to note when we do organic chemistry, there's going to be carbons all over the place, there's going to be hydrogens all over the place, and to save ourselves some drawing time, what we often do is, instead of saying like here, we have a carbon to carbon to carbon 3-cornered ring, instead we just draw a triangle and we just assume right there at that corner is a carbon, here's a carbon, here's a carbon, and then it's going to have however many hydrogens are needed, hydrogen here, hydrogen there, hydrogen here, hydrogen there, etc. And this is a shorthand, what's called line structure way of drawing cyclopropane. Cyclobutane, 4 carbons in a ring, that makes a square, and it's C4H8. Cyclopentane, 5 carbons in a ring, 10 hydrogens, C5H10, and that makes a pentagon. And then cyclohexane, 6 carbons in a ring, 12 hydrogens total, and that makes a hexagon. So one thing you're going to want to do is get familiar with drawing structures, both line structures for simplicity and a more Lewis dot structure to show more detail, and going back and forth between formulas and getting the right numbers of carbons and hydrogens and so on. Okay, the formula relationship in a cycloalkane case is going to be, oops, sorry about that, let's go back to it. Always going to be twice the number of hydrogens as carbons, so 4 carbons, C4, 8 hydrogens, H8, 6 carbons for cyclohexane, C6, 12 hydrogens, H12. Okay, and then here's a bit of a recap, different ways to describe molecules, molecular formulas, tell us how many atoms of each element in the compound, doesn't tell us anything about structure. Lewis electron dot structures give a lot of details about the electrons and bonding. Condensed molecular formulas give us pretty decent idea of structures with less space taken up and less writing as compared to a Lewis dot structure. And then 3-dimensional pictures give us a better image of what they look like, actual and real 3-dimensional space. And then line structures are a kind of simple, quick, fast way to draw things. But that takes a little getting used to for interpreting what they mean. All right. Now, hydrocarbons can also have carbons that have a double bond between them. We still use the main word or main part of the word alk for carbon-hydrogen compounds, but then instead of alkanes, we call them alkenes, E-N-E-S, if there's a carbon-carbon double bond. So 2 carbons would be the F, and then ene instead of ane because we have a carbon-carbon double bond. And notice we don't have 3 hydrogens attached to a carbon, we have 2. So ethene would have the formula C2H4. What would we call this then? Well, let me see. We've got 3 carbons, so that's prop. Propane was the 3-carbon alkane, but this is going to be propene because it has a carbon-carbon double bond. It has 2 less hydrogens than propane, so it's got 3 carbons and a total of 6 hydrogens, so we would call this propene. Now, a little bit about the geometry of alkenes. With the double bond between carbons, that makes them what's called triangular planar, and in class models will be shown for this. But here we can probably see this from an image. If we have a carbon bonded to a hydrogen, and then bonded to a carbon, it's bonded to 3 things, These electron groups are negatively charged where the bonds are, so they repel each other and basically get as far apart as they can in space. And if there's only 3 groups, not 4, the way they get as far apart as possible is actually to make kind of what looks like a triangle, with, in this case, the carbon in the center. So we call that triangular planar. Now, alkanes are what are called unsaturated, alkenes are what are called unsaturated, and alkanes are what are known as saturated. And there is an alkane saturated. Here is an alkene unsaturated. And can you see what's going on in terms of where these terms saturated and unsaturated come from? Well, go back again to the alkane. The difference between it and the alkene is more hydrogens. It's got 6 hydrogens, 3 around each carbon atom, so it is saturated in hydrogens. It's got the most amount of hydrogens you can possibly get around a given carbon atom if there's 2 carbon atoms bonded together. Now, an alkene is not saturated in hydrogens because if there wasn't this double bond, we could have 1 more hydrogen here and 1 more hydrogen there. So you've probably heard of saturated and unsaturated before in the context of fats, but it applies essentially to any organic compound if it has single bonds versus double bonds. And if we have the maximum amount of hydrogens, which means single bonds between carbon atoms, it's a saturated substance, and unsaturated is going to be having at least some double bonds in it. So here we'll jump to fats. This is a molecule of a fat. It's what's called a triglyceride because here is a glycerol, a 3-carbon chain, and then there's 1, 2, 3 what are called fatty acids off of this 3-carbon glycerol chain. So it's called a triglyceride. And don't worry about the double bonds here between carbon and oxygen because saturation depends upon hydrogens. So we look at these carbon chains and we see no double bonds anywhere, so we would say this is a saturated fat. But now here is an unsaturated fat, same glycerol 3-carbon backbone, same 1, 2, 3 chains, same carbon-oxygen double bonds, which we won't worry about. And then for space reasons, I'm only showing the complete one of these chains. The second chain and the third chain here also keep going, but it would be hard to see on the screen because you can see this middle chain here has a carbon-carbon double bond, which makes it bend a bit. And so unlike the saturated fat, the chains don't just kind of line up in rows. It actually gets a little bit more confusing, and there's just not enough space to show this. Point here is there's a carbon-carbon double bond, which means this is an unsaturated fat. It has a double bond, not the maximum number of hydrogens. And in fact, typically this chain would look similar. It would have a carbon-carbon double bond in it, and then same with that chain. So there we go. Saturated fat on the bottom, unsaturated fat on the top. Okay, now let's also consider reactions of some organic compounds other than combustion. All organic compounds are going to burn. The alkanes are very unreactive. They only pretty much burn. But alkenes have a carbon-carbon double bond, and this will be demonstrated in class with models. But basically, the idea is if we have, let's say, ethene, the simplest alkene, carbon-carbon double bond, which would be 2 lines, but that's 2 pairs of electrons, so 2 pairs of dots between the 2 carbon atoms. And hydrogen comes as a diatomic molecule, H2, so H bonded to H, pair of electrons, pair of dots between. And what can happen is, instead of having a double bond between the 2 carbon atoms, carbon can have a single bond, and then those 4 electrons in the double bond, 2 of them go to form bonds with hydrogen. One of them bonds with one of the hydrogen atoms, one of them bonds with the other hydrogen atom, and it basically is just a rearrangement of these 2 molecules to make, in this case, the molecule ethane with a carbon-carbon single bond, and the hydrogens have been added across the double bond of the original ethene. So you can kind of track this. The open circles here represent what electrons were originally part of hydrogen, and you can see how it's now sharing, this hydrogen atom is sharing electrons with this carbon, one of its electrons and one of the electrons in the carbon-carbon double bond, and then same over here. And this is a thing that generally happens with carbon-carbon double bonds. Here now we're just showing it with bonds, not with electrons, is one of the bonds in the double bond breaks, the bond between the H and the H breaks, and then the H, one of the H's adds onto here, one of the H's adds onto there, and we still have carbon with 4 bonds, but now the hydrogens are attached and there's no longer a double bond. Notice also this made an unsaturated hydrocarbon a saturated hydrocarbon by adding hydrogens, by saturating it in terms of the hydrogens around the carbons. Now this can happen with other things. For example, water is H2O, and if we look at water as an H bonded to an OH, well, this is pretty much like an H bonded to an H, except the second thing isn't another H, the second thing is an OH, but once again, the double bond can break, or one of the double bonds can break. The bond here between hydrogen and oxygen rather than hydrogen and hydrogen can break, and then this hydrogen attaches to that carbon, and this oxygen attaches to this carbon. And if we add ethene to water, then we get this structure. It looks almost like ethane, except one of the hydrogens is an OH group instead of an H. This is what's called an alcohol. Actually, specifically, it's ethanol, which is the stuff that's in beer and wine. And ethanol, which is also called ethyl alcohol, is an ethane, so 2-carbon alkane, but with an OH group, and an OH group makes it what's called an alcohol. So alcohol means OH group. And this is showing the reaction we just talked about in somewhat simplified form, not showing the structures as well. And this is generally what happens. Adding water to an alkene will produce an alcohol, and this is true if we have longer carbon chains as well, but we're just doing a couple simple examples for introductory purposes. Now, a similar reaction can occur between an alkane and something like a halogen, like chlorine. So when a diatomic chlorine molecule reacts with an ethene or any kind of alkene, one of the bonds in the double bond breaks, and one of the chlorine atoms attaches to this carbon and one attaches to that carbon. So now we have 2 carbons bonded with a single bond between them, and then each of these has a chlorine attached. And this is the reaction of ethene with chlorine, and it makes a compound called 1,2-dichloroethane. And maybe let's look at the name just a bit. Ethane means we have 2 carbons, and chloro is chlorine. Di means we have 2 of them. And then the 1, 2 means if we call this carbon number 1 and we call this carbon number 2, this means we have 1 chlorine on carbon number 1 and 1 chlorine on carbon number 2. If we had both chlorines attached to the same carbon, then we would call it 1, 1 dichloroethane because both chlorines would be attached to the same numbered carbon. Okay, next up, we have single bonds, alkanes. We have double bonds, alkenes. That's between the carbon atoms, of course. And we can also have triple bonds between carbon atoms. And when we have a hydrocarbon with a carbon-carbon triple bond, these are called alkynes. And here's an example of a carbon-carbon triple bonded compound, two carbon atoms with a triple bond between them. That leaves only one more bond, so carbon bonds to one hydrogen here, and the other carbon bonds to one hydrogen. The formula is C2H2. This is called ethine, so two carbons means eth, and then if it's an alkane, a single bond, it would be ethane. If it's a double bond, it's ethene, and if it's a triple bond, it's ethine. And also worth noting, the common name for ethine, not the systematic name, is acetylene. And you've probably heard of acetylene before. It's used in welding and cutting torches and things like that. It burns very, very hot. So here is an example of somebody welding with an oxyacetylene torch. Oxygen and acetylene are mixed together, so the fuel and the oxygen needed for combustion are together and burns very hot and provides high enough temperatures to melt metals so they can be welded together. Now, quick thing to note about the geometry of an alkene. We have a triple bond between the two carbons and then only a single bond on the other side, in this case to a hydrogen. And if we only have two groups of electrons, the triple bond counts as a single group. They end up on opposite sides of a molecule, and the molecule actually is straight or linear. And models of this will be shown in class, and you might get a chance to make some models as well. Now, we'll move on from the more simple, what are called straight chain alkanes, ones that have carbons bonded one to the next, to the next, to the next in a line. And note that we've seen this already with cyclic compounds, is that the hydrocarbon can sometimes have a ring of carbons. And if we have a ring where we have single bonds and double bonds alternating, and it's a six-membered ring, this is a very common thing to happen actually in chemical compounds. And this is called a benzene ring, the six-carbon ring. Here's the line structure for it, a hexagon with alternating single lines for single bonds and double lines for double bonds. And hydrocarbons that contain a benzene ring are called aromatic hydrocarbons. And as you might guess, the name aromatic comes from the fact that a lot of benzene ring containing compounds have a distinctive aroma or smell. Here's one more way to draw the line structure of benzene. It's really not single bonds and double bonds alternating. It's really kind of like 1.5 bond in each location. And so sometimes we draw a circle in the center instead of 3 lines. So the origin of the term comes from the fact that a lot of these have a smell or aroma. And in class, we'll have a few aromatic compounds, benzene ring containing compounds for you to smell. Some smell good, some smell, well, let's say not so good. Okay, now so far the organic compounds that we've looked at are hydrocarbons, just carbon and hydrogen, and they are very nonpolar, and because they're nonpolar, they don't dissolve well in water, which is polar, and we call these hydrophobic. Hydro means water, and phobic means does not like. So nonpolar compounds don't like water, don't dissolve well in them, because they are nonpolar and water is polar. And what we find in general is that compounds with similar types of polarity dissolve better in each other. We often say like dissolves like. Now, some compounds organic compounds, may contain an oxygen or a nitrogen or other elements which do give polarity. So if we have an oxygen bonded to carbon, that is a polar bond. It has a separation of charge, a positive end and a negative end. And if they're polar, then they do dissolve in water. Depends on how polar as to how well they dissolve in water. But things that are reasonably polar dissolve quite well in water. And we call these things hydrophilic, as in they are water-loving as opposed to water hating or water being afraid of. Some hydrocarbons that contain a hydroxyl group, an OH group, we've seen this already as a product of an alkene reaction with water, are called alcohols. So here is a 2-carbon compound, but one of the H's, if it had been ethane, one of the H's is an OH group instead. All right, moving on to some more complicated compounds. This is a willow tree, and the bark of the willow tree contains a molecule called salicin. Here is a molecular structure of salicin. You can see a benzene ring here, and you can see an OH group here and there and there. So it's, and here's one more. It has the properties or the group that alcohols contain. And then here's a C double bond O OH group. So this is a much more complicated molecule and has a number of different groupings that are commonly encountered in organic compounds. From salicin, and the bark of the willow tree used to be given to people as sort of a pain reliever because of the compound salicin, which has those kinds of properties. We can take salicin and essentially chop off part of it. So if we leave this behind and chop off all of that, we get something called salicylic acid, which also has pain relieving properties. And then we can do some further modifications of the salicylic acid and add what's called an acetyl group here, and we have something called acetyl salicylic acid. And don't know if you've ever heard of acetyl salicylic acid, but you've probably heard of it by its more common name, which is aspirin. Okay, so a little bit more on one of our groups of compounds, alcohols, and other compounds as well. So this is a chart that is on your handout, and these are examples of what are called functional groups. Alcohols are a functional group if we have a compound that contains carbon and hydrogen stuff and then an OH group, we call it an alcohol. The example we've seen before is ethanol. It's got a carbon and a second carbon. That's the eth part, 2 carbons. And then 5 hydrogens, 3 on this carbon and 2 on that carbon. And then an OH group instead of a third hydrogen on this carbon. That makes it an alcohol. So we call it ethanol or ethyl alcohol. And then just as a note, we could have had 2 carbons here, we could have had 3 carbons, we could have had 1, we could have had fairly complicated things like in our salicin molecule, where here's an OH group connected to a whole bunch of carbon hydrogen stuff. And we often use the symbol R essentially just to represent a bunch of carbon stuff. So other functional groups, other things that are encountered are a bunch of carbon hydrogen stuff attached to, here X represents a halogen molecule like chlorine or fluorine or bromine, etc. So this is a molecule of chloroform. It's actually got 3 chlorines attached to a central carbon. And whenever we have, we would call this an alkyl chloride. And if we had bromine here, we'd call it an alkyl bromide. And so when we have a halogen attached, it's going to be, went ahead a little, it's going to be a halide. Phenol is a benzene ring with an OH group. Thymol, here's an example of a type of phenol. Thymol is a compound that's added as a preservative to eye drops and things like that. Ethers are carbon stuff on one side, carbon stuff on the other side of an oxygen. And you've probably heard of ether as an anesthetic. Used to be used, but had a lot of problems with its side effects of causing nausea and being very flammable, so it's not really used now. But it was the first anesthetic that was used. That was actually diethyl ether. This is a molecule of dimethyl ether. Aldehydes contain a C double bond O bonded to H, and then that's bonded to carbon stuff. Here's a molecule as an example of acetaldehyde. Ketones contain a carbon but double bonded to oxygen with carbon stuff on one side and carbon stuff on the other side. And this is actually a diketone as an example here. Carbon bonded doubly to oxygen. Second carbon doubly bonded to oxygen. Most ketones only have one carbon-oxygen double bond. And then carbon stuff on each side. This is called butane-dione. It has kind of a sweaty smell. Carboxylic acids contain carbon double bonded to oxygen and then bonded to OH. If you ever see that group, you recognize the molecule as a carboxylic acid. And an example we've already seen is salicylic acid. Esters have carbon double bond O bonded to O and carbon stuff on both sides. So here is an ester group, C double bond O to O, carbon stuff on this side, carbon stuff on that side. It's called ethyl butyrate. It smells like pineapples. Amines have an NH2 group. So here is an NH2 group with a bunch of carbon stuff. This molecule is called putrescine, and it's smelly. It smells like rotting flesh. It's a really nasty smell. Amides contain an NH2 group like an amine, but that's bonded to a C double bond O, and then that's bonded to other carbon stuff. So we're looking here for something that is an amide, and so here we have an NH. Here we have an NH group bonded to a C double bond O, and then carbon stuff on both sides of this. And this is aspartame, and you probably know it by its trade name, NutraSweet. And you don't have to memorize functional groups, but you'll have a table of functional groups available to you, and you should be able to identify functional groups in molecules, especially with the help of a table like this. And why don't we say that's enough for 1 day's worth of lecture. So that's the end of this screencast. Work on the homework, get your questions ready, and we'll finish up the organic chemistry chapter and have plenty of time, I think, to answer questions on things and help folks with stuff as well on Tuesday's class.